So with the question here addressed on supply, let's shift a little bit to ask the question, well, how are we doing on groundwater quality? And when it comes to, in this country, national groundwater quality, no one better to ask than Ken Belitz, who is leading the National Water Quality Assessment Program for the USGS, and has also is very steeped in, is coming from California, is very steeped in California problems both on the supply and the water quality side. And is one of those people that I'm always amazed at just how many things he can fit into a day, and all the things that he's running. And he will give us an overview on how we're doing with U.S. national water quality in agricultural areas. Welcome, Ken.
Thank you. It's unusual when I speak about the United States that I'm reducing scales compared to what we've just seen. I've italicized the agricultural area part of my talk because I'm going to speak more broadly, but I'll kind of touch on agriculture as I go. My talk will have 4 parts. The first part is just to kind of set things up. When I was asked to participate, I'm one of those people who works technically and don't spend a lot of time thinking about sustainability. I want to spend a fair amount of time on a concept about equal area grids and try to develop some intuition for you so that you have a better understanding of how we're trying to make some assessments. I'll give you one small example from California. Perhaps you'll find it surprising, perhaps not. And then I'll focus on what it is the USGS will be doing over the 10-year time frame, 2013 to 2023. I went back and looked up the original definition for sustainable development from the Brundtland Report. Development which meets the needs of the present without compromising the ability of future generations to meet their own needs. So how do we measure that? And it occurs to me that if we're going to measure sustainability, we need metrics. How do we know how we're doing? Where are we now? If we look at the future, how do we compare it? So I'm going to focus on this metrics part, not on the practices that lead to sustainability. There are a number of questions, then, that one can address with respect to water quality. Which constituents are most prevalent at high concentrations? And I want to emphasize that word most, because you can get a long list of things, but they're not all equal. When we talk about high concentrations, we'll compare them to health-based screening levels, and Patty Toclino and others at the USGS maintain a website where there are regulatory and non-regulatory health-based thresholds. You can define a high concentration as above a health-based threshold, or at half of a threshold, or a tenth. It really doesn't matter. It's a metric. Once we look at those constituents, we can ask which areas are most affected by those constituents. So there could be a basin or a group of basins or a state or a continent, and one can begin to assess what proportion of those areas might be high. And then finally, how many people are potentially affected by those constituents? And we try to frame this through how many people or equivalent people are dependent on groundwater, what are the proportions or the detection frequencies of groundwater with high concentrations, and translate that to an effective number of people, and then back towards proportions. So that's sort of the setup. Metrics allow us to make a measure of system state. We can look over time, see how that system state has changed, and have some sense how we're doing. I want to introduce this idea of equal area grids. Perhaps this is obvious, perhaps it's subtle. We have a groundwater domain. We can lay down a grid. And we're going to sample across it. We're going to try to infer from our samples what the proportion is of high concentrations. Well, just for the moment, let's go the other direction. We've got a grid. It's 10 by 10, 100 cells. 9 of those cells are high. We're going to obtain 1 groundwater sample from each one of those cells in equal area grid sampling. In this highly structured case, we're going to get exactly 9 dark samples and 91 clear samples. The proportion's 9%. You have no choice, right? So far, so good. Well, let's take those 9 dark cells, and let's shift them from the upper left-hand corner to the center. Stretch them out as a line across the top, or simply spread them around. Sample 1 well per cell, 100 samples, exactly 9 high, 91 clear. It's still 9%. So it doesn't matter where that target is located. It doesn't matter how it's distributed. In essence, we've done with an equal area grid cell the equivalent of a well-mixed urn. We've sampled all parts of the aquifer, and we've obtained a spatially unbiased estimate of that proportion. Well, let's just generalize from those 9 cells. Instead of a 3 by 3, it's a 6 by 6. And you look at one of those gray cells, divide it up into 4 parts. 1 dark, 3 white, or divide it up into 16. 4 dark, 12 white, or clear. Now let's sample 1 well per cell. Let's start with those white cells. You will get exactly 64 clear or white samples. You have no choice. Now you go to these 36 cells. There's a 1 in 4 chance it'll be dark, a 3 in 4 chance it'll be clear or white. Odds are, on the average, you'll get 9 out of those 36, but you can get more, you can get less. The chances of getting no dark cells is very small. The chances of getting 36 dark cells is even smaller. So the uncertainty increases as we spread that target around. Right before we had a 3 by 3, perfectly structured. Now it's 6 by 6. We introduce a little bit of uncertainty. Well, let's just take the whole thing. So now we're looking at that little box labeled K. I'm not sure how well that shows up on your screen. The entire domain is gray there. So there are 100 cells. Every cell is gray. Inside that cell, it's 9% dark and 90% white. Collect 1 sample per cell. There's a 9% chance of getting a dark sample in each and every cell. It's the exact same story that you're going to, on the average, get 9, on the average 91, but you can get more or less than 9. So the most likely outcome is 9 dark. The uncertainty, again, is increased. Well, so if we have a well-structured grid, we have a highly structured feature like the 3 by 3 or even that 6 by 6. But in essence, we're really dealing with a gray box, right? We don't really know what's there. We're obtaining samples, we're drawing an inference. Well, in addition to a design, 1 well per cell, we can also use these grids for declustering. So what you see in I in those little black circles is 1 value per cell, equal area sampling. Doesn't matter which one you pick, because it's all gray. And then there are other wells also available to you. In essence, what we can do in every cell, we can use whatever available data we have in that cell to draw inference about that cell and then round it all back up. So the grid also provides sort of a weak geostatistical declustering algorithm. Okay, so let's summarize on this aquifer scale proportion. It's independent of the distribution of high concentrations. That may be bothersome to you. It just doesn't matter. The aquifer is a gray box from which you're sampling. It doesn't depend on the shape or the location of the target. The precision of your estimate does depend on the number of samples that you have and also on that distribution. If it's 1 value per cell, it's a relatively straightforward computation through the Jeffreys interval. If there's many data in some cells, few data in others, then it's a little less straightforward. This may be subtle, it may be obvious. Proportion is scale invariant. It does not depend on the size of the area that you're trying to make an estimate. You can talk about groundwater quality in New Jersey. You can compare it to groundwater quality in Texas. Just because New Jersey is small, if you have 100 samples in New Jersey and 100 samples in Texas, you have the same level of precision in making an estimate of proportion. Therefore, areas of different size can be compared because it's non-dimensional. It also allows for comparison of disparate constituents. Every well could be coded. Was the sample that we obtained high or low with respect to an inorganic? Was it high or low with respect to organic? So we can go through an exercise where we've sampled for hundreds of constituents, and we can ask this question at a really broad scale. Are inorganic constituents high, or are organic constituents high? If we take that inorganic term and break it out, are trace elements high, or is nitrate high? We can take that trace element, is uranium high, or is manganese high? Manganese has a secondary maximum contaminant level in the United States, but it also has a health-based screening level. It's tied to IQ in children. Okay, so that's the equal area grid. It's a sort of a subtle concept or an obvious concept, depending upon where you're looking at it from. But it's an underlying concept that we use in NAWQA to make evaluations. It's also a concept that we use for the Groundwater Ambient Monitoring and Assessment Program, which was sponsored under the State Water Resources Control Board. The fundamental unit analysis, then, is the equal area grid. So this is the Cahuilla study area located in the San Joaquin Valley. There are 20 equal area cells. They look like jigsaw puzzle pieces. It's not a perfect grid. But what we've done is taken that domain and we've stratified it into equal area cells. All areas of the aquifer will count equally. Shown in those gold circles are the 1 well per cell that the U.S. Geological Survey sampled. Shown in X's are additional data available from what used to be the California Department of Public Health database. Now it's with the Water Resources Control Board. We're trying to draw an inference at the scale of a single study area, but we can take many study areas and bring those results up. A study area has an area. We've estimated its proportion. We therefore know the area that's high. Take the next study area, round it all back up, and we can recompute proportion. We can also weight those areas by the population served by groundwater. Here we have the San Joaquin Valley and the Sacramento Valley. Hopefully I'll get this. Great. The San Joaquin Valley, Sacramento Valley contact is just about there. There are 16 study units in here. The colors are because we sampled several study areas at a time. This feature here is right here. So there are 16 study areas. We had about 3,000 wells available in the San Joaquin Valley to do this kind of work. We've also done this for the state of California. I won't share the California results today. 87 study areas, about 11,000 wells. So we can now ask the question for the San Joaquin Valley, one of the most productive agricultural provinces in the world, which constituent class is most prevalent at high concentrations, in this case above the health-based screening level? The y-axis is proportion. Let's take a look at trace elements. 16 study areas. About 22% of the area has high concentrations for one or more trace elements. If instead we weight all those areas by their population, and we're relying on detection frequencies in that case, about 12 or 14% of the groundwater, as seen by people, has high concentrations. Nitrate has about 5% prevalence at high concentrations by area at the depth zone used for public supply. You've heard some presentations about domestic supply. There's a much higher level of concentrations of nitrate in that shallow zone. The population weighted estimate is quite close to the area weighted because people are relatively well distributed amongst those areas. Perhaps what's also surprising is organics. It's only 2 or 3%, which is actually high for California by area, but it's 5% by population. That's largely DBCP, which is a legacy fumigant. So organics with respect to people are as impactful as nitrate. But trace elements as a class are the most prevalent constituent group. Perhaps that's a surprise. We've been talking about this for some time, so it may not be as much. This work you can find in a recent paper in Environmental Science and Technology. The basic underlying math is also in Water Resources Research. So finally, let's look at our NAQUA design. Principal aquifers will provide a framework for assessment for the USGS. Here you see in various colors 20 principal aquifers. Collectively, they account for 90% of pumping for public supply in the United States and 85% of pumping for domestic supply. About 45% of the drinking water in the nation is groundwater. NAQUA has 3 scales of studies. In our first 20 years, we've primarily focused on land use studies and major aquifer studies. The thickness of those maps is roughly proportional to the depth interval sampled. Our land use studies either focus on agricultural land use or urban land use. They're typically observation wells. They sometimes include domestic wells. They're 20 to 50 feet deep. We'll be sampling about 1,400 wells over that 10-year window. Our major aquifer studies are typically domestic wells, but sometimes include public supply wells. The well perforations are typically 50 to 150 feet beneath land surface. We'll be sampling about 1,200. Our principal aquifer surveys are public supply wells. A typical screened interval is about 150 to 750 feet deep, and we'll be sampling about 1,500 wells. The U.S. Geological Survey samples for a really long list of water quality constituents, that is those primarily with health-based screening levels, but a lot of the pesticides and their degradates, a lot of the VOCs don't have HBSLs. A lot of these have geologic sources, a lot of these are anthropogenic sources. A hallmark of NAQUA are low-level detection methods. The USGS also samples for new analytes, sometimes called emerging constituents. We're sampling every supply well we go to, whether it's domestic or public supply, for a long list of pharmaceutical compounds, hormones, microbiological indicators, a lot of these are new, a long list of radiochemistry, and unconventional oil and gas markers. We routinely sample for geochemical indicators, major ions, redox, pH, dissolved oxygen, and temperature. And then a hallmark of the program is an exhaustive suite of H tracers: tritium, SF6, CFCs, carbon-14, and the noble gases. How does NAWQA assess trends? Bruce Lindsay gave a presentation yesterday talking about our decadal scale assessments. But a really important question to ask is, over what time scales does groundwater quality change? So we have our decadal sampling of the major aquifer system and land use study networks. We have a new type of network we're calling enhanced trends networks. We're trying to assess over what time scales groundwater quality changes within a 10-year window. We also have what we're calling vertical flow path studies. We're using H tracers, sampling wells at multiple depths over a relatively wide area to get at the timescales greater than 10 years. Well, those aren't the only data that we have available. These are data collected by the USGS. A lot of ancillary information is collected. A lot of water quality constituents are collected. H tracers are collected, all expensive. But there's also the National Water Information System data set that the USGS maintains. We've recently put together 27,000 sites, and we've mapped potential groundwater corrosivity. That work will be published on July 12th. In addition to those 27,000 data points that we have available, there are 250,000 community water supply wells in the United States that are required on the average to sample every 3 years or so. But there are more than 500,000 sites in that data set. We're systematically working with the states to assemble these data up. So, to summarize, assessment of sustainability requires metrics. That's one of the things that we can do at NAWQA to help evaluate sustainability. Equal area grids provide a quantitative basis for assessing groundwater quality, both for sample design and declustering. The National Water Quality Assessment Project uses equal area grids, targeted studies, and modeling for assessment of trends and status. I have not spoken really about those targeted studies and modeling today. And with that, I'd be happy to take questions.
Any questions?
It's an excellent talk, and thanks for sharing this information. I think the USGS is the leader looking from the ground. So I was just wondering that with the technology changes, with all this, because satellite imagery, they are sort of automated, but do you have any automated way of collecting this data, with this large amount of data in the future at least?
The enhanced trends networks that I was talking about, we have 8 sites, 3 wells per site, and we are continuously monitoring specific conductance, dissolved oxygen, temperature, pH, and at several of those sites, nitrate. And then on a bi-monthly basis for a period of 3 to 4 years, we sample for a full suite of constituents, and then once a year for a period of 6 to 7 years, we sample as well. The issue of automated sampling is really challenging because if you put a probe in a well, you're not just sampling groundwater. You're sampling this water in the well, which is some kind of a hybrid between the groundwater and the standing water. So we are either instrumenting domestic wells and public supply wells, in which case we've got equipment outside, or we are actually pumping the well on a daily basis remotely and then monitoring it. The development of that has been a challenge. It took about 2 years for us to develop those sites. And so then it's all telemetered and it's all can be observed from the office. But it's a challenge to keep that equipment monitoring what is groundwater as opposed to something else. In the back.
Thank you for the presentation. I didn't really get how the equal area grid handled the 3D quality of the groundwater, and that long screens may mix groundwater of different quality.
Yes. The key is stratification. So if you have a set of observation wells, you're not mixing those with domestic wells, you're not mixing those with public supply wells. So that 3D aspect is handled through that stratification by depth. With regard to mixing, the depth zone used for public supply is the depth zone used for public supply. And so that's the water extracted at that point. So it is true that you're getting that mixed signal, but it's the mixed signal that we're extracting.